Now. Okay, hello everybody. Welcome to lecture number 10 and welcome if you're joining us for the recording. So our business at the moment is we're just about finished with chapter 1, the content and integration. Keep an eye out on the website. Today, later, I'll post a few more supplementary examples on the week 5 page about the improper integrals that we were talking about yesterday, if you're interested in looking at a few more examples of that. The current homework sheet, as you know, the second one is due tomorrow, and possibly the examples from the recent couple of lectures would be of interest to that, as well as some of the supplementary ones if you want to have a look at them. I wanted to say a few words, I suppose, because we're at a kind of a milestone in the course, the conclusion of chapter 1, and on integration and techniques of integration. So just a few words about that, and in particular, I suppose, relation to the assessment for the module. So the first exam question, which will be coming up in due course, I suppose, is it's going to be based on chapter 1. So I think I've said this before, but in the end of year exam, we'll have 3 questions in the calculus section. There'll be 3 also in the algebra section, but the 3 calculus questions will basically deal with the 3 chapters of the lecture notes. So the first one will be based on chapter 1. And I'm very aware that, you know, you haven't had an exam session yet and that we have, unfortunately, not the opportunities that we would like to have for communication, either in scheduled settings like this or even informally that we would typically have, and also that you didn't have an exam session in the winter. So that, you know, I think this is especially tough on our first year students this year who haven't already been through an exam session in previous years and haven't really had the opportunity to interact in person at all. So I'm very aware that, you know, that it's necessary that we would have a good awareness of what to expect when it comes to the exam. So I'll be, you know, as the course goes on, we'll be talking about that quite a bit, and we'll have some sample exam type problems and so on. So at this point, because we're at the end of chapter 1, maybe it's time to useful to comment on what maybe to expect in chapter 1. So I suppose the learning outcomes for chapter 1 are concerned with being able to implement the techniques of integration and being able to say something about the fundamental theorem of calculus and what it means. And I suppose being able to recognize what technique applies to a particular example. So the first question on the exam will basically resemble the sorts of questions we've had on the first 2 homework sheets. You know, there'll be a few examples of integrals to determine, to evaluate, definite and indefinite integrals, maybe an improper integral, involving the main techniques that we've seen: substitution, partial fraction expansions, integration by parts, and there'd be some part of it that would be about interpreting the fundamental theorem of calculus, the area accumulation functions and their derivatives. So I guess, you know, when you're thinking about studying the subject in general, and in particular, I suppose, preparing for answering that exam question when the time comes, the things you need to do are just really practice the techniques of integration. And for that purpose, I think it's certainly useful to pick up a calculus textbook, the one by Stuart, which is linked from our homepage, is certainly a useful one, and work through some of the examples there, some of the questions, and you know, you have the opportunity, if you want, to check the answers with the ones that are given at the back of the book. So if anybody is looking at that and would like, you know, any particular advice about sections to look at or anything like that, I'm more than happy to engage on that. The other thing that I just want to mention is that at the end of the lecture notes in each section, there'll be a short section about exam advice for that particular chapter. So at the moment, let me share the current lecture notes for chapter 1. So here it is. Hopefully you can see that, the section 1.6 of the lecture notes. So basically just at the end of each chapter of the lecture notes, there'll be a section with just exam advice and, you know, a sample question. And so I have to apologize. I didn't realize until yesterday that the version of this that was posted in the chapter 1 lecture notes wasn't complete. It was some kind of partially completed draft, which was accidental. So I've updated it yesterday. And so a new version of the PDF for chapter 1 on the lecture notes was posted yesterday evening, and it has a sort of slightly more complete version of this section 1.6. So basically, it's got a sample sort of exam type question. And, you know, here it is. It's got a part about the fundamental theorem of calculus, sort of typical example about that, you know, where maybe there's one of these area accumulation functions, advice to, you know, a few questions to asking you to show that you understand what's going on here and what the fundamental theorem of calculus says about the derivative of this area accumulation function, and then a few integrals to evaluate or to calculate. And as you can see here, this is very typical. Like, you can have a look back at old exam papers, which are similar in style, And, so there'd be an example involving a substitution, maybe an integration by parts example. Here, there's a partial fraction example, an improper integral example. There's a solution to each of the 4 parts here. And what I've tried to do with the solutions in this section is, rather than kind of give a fully detailed explanation with sort of narrative, I've tried to kind of give a sort of a shorter version that I think would be suitable as an exam answer, where I know that there are time constraints and people are under pressure, and it's not really quite the same as a kind of relative explanation for your own notes. So I suppose when I give a sample answer here, it's kind of what I would expect to see in an exam answer that I would consider to be sort of perfect if I haven't made any mistakes, which is entirely likely. But, this is kind of the level of detail that would be kind of ideal in an exam answer. It doesn't mean you have to write it exactly this way or use this form of words or anything like that. It's just supposed to kind of give an indication of what level of detail and what level of explanation I would like to see in an exam context. So I mean, if this is helpful, let me know. I can add a few more examples. I can add a few examples without answers or without solutions for you to think about yourselves. Certainly there are loads of examples also in old exam papers. But I suppose what I want to say really is that, we will have time to discuss what to expect in the exam and what would constitute sort of a good answer. And the other remark I'd make is something that's unusual this year and different from other years, well, not different from last year, but different from most years, is that, the exam will be online. That's complete. That's clear now. I think it has been decided, even if it hasn't been officially announced by I'm not sure if it has been officially announced by the university, but it's certainly it will be the case that the exam will be conducted online, which means that everybody will be working on it at home. And it means also that your lecture notes will be available to you during the exam. So the pressure, I suppose, is slightly less to kind of have everything at your fingertips. You will be able to try to check the techniques, check the integration by parts formula, these sorts of things during the exam, have a look at the notes and so on. You still have the time pressure, so you don't have time probably to, engage in long reading of something, but you do have the opportunity to refer to our notes, for instance, during the exam. So I hope that even despite the very imperfect communication facilities available to us this year, that we'll have time to talk about these things and that you'll have time to prepare in a reasonable way. And hopefully that it won't be, hopefully that we'll be able to relieve some of the sort of stress of the exam session that way by being well prepared and having a good idea of what to expect in terms of format. So I suppose the main point for now is that that's there. Section 1.6, I can augment it if it would be helpful, just let me know. It's at the moment one exam type question, but we can add a few more if that would be useful. What else do I have to say right now? Nothing really, except that this is we're at this kind of milestone sort of turning point in the course. We're going to move on to another topic. So I suppose in terms of the techniques of integration, I think the best way to learn them is by practicing them yourself. So you've had a good few sessions of watching me working on them. So, make sure as we proceed that you sort of keep practicing them, I suppose, even though we'll be moving on to other topics. Does anybody have a question or comment about any of that right now? We will have time, later in the course for a review of everything and a couple of kind of meetings maybe where we can specifically prepare for the exam as a whole, but maybe at the end of each chapter it's worth having a look at what to maybe expect in the corresponding question. So this is not the final word in this topic. We'll have time to review again in the later weeks, in the last couple of weeks of the semester. Exam set for April or May. Good question. The dates for the exam session have been announced. I don't have them in the top of my mind, but I think it. But hang on, no, lectures continue until May, so it's the second half of May most likely. I'm not sure whether the exam session actually runs into the month of June or not, but the exam timetable will be released later, and it hasn't been yet, so we'll know a little bit later, and I'll know at the same time as you will. Thank you. Exam starts the 18th of May. Okay, so more than likely it'll be in the second half of May. It might be into the month of June. Usually this happens fairly early in the exam session, but not always. So we'll all find out at the same time when the exams office announces the timetable. Shouldn't be too much longer, I think. Okay. Thanks for that, everyone. Okay, so if anybody has a question, please ask or put it in the chat. If not, we'll move on. And come back anytime if you do have a question. So I'll close that one and maybe move on to talk about something new, which is chapter 2. Okay, so hopefully you can see the start of the lecture notes for chapter 2 of the real numbers. If you can't, please complain loudly in the chat or on the audio. So, okay, so chapter 2 is called the real numbers. And in a way, we're going to be looking back at some elementary things that we've known about for a long time, but we're going to be looking at them probably in a bit more detail. And I suppose one of the themes here is, yesterday we finished chapter 1 on the topic of improper integrals, which was looking at things like, areas of regions that are sort of infinite in one direction, things like that. And so it was beginning to kind of address the topic of dealing with concepts of infinity, which is really going to be a theme for us in chapter 2. We're going to start in section 2.1 by looking at the real numbers, which are in a sense sort of the theme of study in calculus and in analysis, and how they differ from other number systems that we know about. So I suppose maths is divided up into a bunch of different subject areas, which have a lot of overlap and a lot of links, but they're regarded as being sort of separate. One of them is the subject of analysis, which is, I suppose, kind of the theoretical side, the theoretical end of calculus, and that really is concerned with the real numbers, in the sense that number theory, for example, is really often concerned about integers and about properties of integers and properties of prime numbers and things like that, which is not to say that people don't use ideas from number theory and analysis in both areas and in conjunction with each other. But like if the things you want to know about are, for example, prime numbers, then you're sort of doing number theory. If the things you want to know about are continuous functions and properties of real numbers, you're sort of doing maybe analysis. And so we have lots of different number systems. We have the integers, which are whole numbers, and probably the first ones that most of us met, at least the positive integers. We have the rational numbers, which are fractions, and which are the numbers that we really use in computations and in calculations when we're using like decimal representations of numbers. We're probably using rational numbers because we probably are using sort of truncated decimals. And there's the real numbers, which are sort of something else, and which include more than just the rational numbers, and those are our concern in this course. And obviously there are things also, like I know in algebra you're studying things like modular arithmetic, and with Graham in semester 1, and that's another whole area of kind of number systems that are quite different from the real numbers. So there's lots of different number systems that we like to think about, and we like to think about the kind of philosophical definitions behind them and about their properties and about how they resemble each other and how they differ from each other. And our theme here is the specific example of the real numbers. So I suppose one remark that I'll make is that in the first chapter, when we were talking about integration, the kind of key activity there is to practice techniques of integration. And you can do that by giving yourself examples, or by me giving you examples, or by picking up examples from a book and finding antiderivatives and implementing the techniques and practicing that until you're really accomplished with it, which is really, which is our goal in integration. This is a bit different because instead of kind of thinking about how we do something, how we get an answer to some question about finding an antiderivative or whatever, we're kind of more thinking about these kind of concepts of properties of number systems. And so it's a little bit more nebulous in one way. And it's a little bit sort of less clear, I suppose, what we should be doing to get fluency in this and to get kind of expert knowledge in it. So it's a little bit more sort of, thinking about concepts, observing properties, kind of asking ourselves, what's going on here really? Is this example different from that one, or is it similar? And so there's a little bit, it's a little bit harder to kind of learn it by working on exercises, or by on the other hand, having said that, there are certainly questions that we can ask ourselves and try to answer that can build our understanding of it. So I suppose if you find it a bit different, don't let that kind of unsettle you. It is a bit different, and it is kind of a little bit more. I think the fact it's a bit more, what we can actually do to learn this is a bit more kind of reflection and thinking about things and coming back to them. We can't, it's a bit harder to sort of work through 10 examples of integration by substitution and say, okay, I've got the hang of that now. It's not really like that. It's more thinking about something, understanding it a bit, then coming back to it, understanding it better. And it's a bit like that. But anyway, we will have plenty of tasks to do to keep ourselves focused. So let me know how it's going for you, and if you find it interesting. Okay, anyway, what we're interested in here is a few things. Like, set of real numbers, what is it? First of all, it's a pretty abstract concept, really, even though we've used it a lot. And real numbers are not the easiest things to really get your hands on in a concrete way, but we use them all the time. We think about also the set of rational numbers, which is a more familiar thing, really, and a thing that we work with all the time, even though we're probably not thinking about the properties of rational numbers while we're working with them. And the set of integers, which is more familiar to us from throughout our lives of learning, and other related sets. So we'll be asking ourselves, what's special about R? What distinguishes the real numbers from the rational numbers? why is the set of real numbers such an interesting thing that we devote all this energy to studying it? Okay, a fair question, and we'll try to give some kind of answer to it. Okay, so the set of real numbers is denoted by this R, and I suppose something I should mention is this font that it's written in is at this stage a very standard thing in mathematical typography and mathematical communication. It's this kind of, it's called Blackboard Bold because it's a version of boldface that was supposed to be writable on a blackboard. But the way it's usually written by hand is you write a capital letter R, but write kind of an extra stroke down the left-hand side of it. So it looks like that. So it's an R, but it's specifically the R that's the symbol for the real numbers. Similarly, for the Q of the rational numbers, I usually write it like this if I'm writing by hand, kind of like a capital letter Q, but with this kind of vertical stroke down the left-hand side, just to indicate that it's the system of rational numbers. It's not just the letter Q. And the Z of the integers, I usually write a kind of extra stroke down the diagonal part of the Z like that. This is not so important. It's just a way of communicating in writing. I mean, if you just write an ordinary Z, people will more than likely know what you mean. But it's a kind of convention, I suppose, of handwriting that has also made it into typesetting. Okay, so that's the R, Q, and Z of the real, rational, and integers. And we're going to be able to, one comment that I make is we need to be familiar with these symbols and sort of train ourselves to recognize them instantly without having to kind of remind ourselves which one is this, if we can. Okay, what is the set of real numbers? That's the thing we want to focus on. But in order to answer that question, a good place to start is with the integers, which are more familiar to us, I suppose. So I assert that there are at least two useful ways to think about what real numbers are. There are probably more than that, but there are two of them that I find very useful. They're kind of a bit different. One of them is sort of geometric, and the other one is kind of arithmetic, I suppose. So we're going to work towards that. But first of all, we're going to start at the start of the story, really, in terms of development of number systems with the integers. So integers are whole numbers. And the set of integers is denoted by this boldface Z. The notation comes from the German word Zahlen, I think, which is the word for numbers in German. So the Z is the set of all positive and negative whole numbers and zero. Okay, so if you want to start back sort of even further, we'd probably start with the natural numbers, which are the positive whole numbers, and they would have been sort of invented for the purposes of counting, I guess, independently in many civilizations throughout the world. So the integers, include all the positive and negative whole numbers and zero. So they're ordered sort of from the negative side to the positive side. There's obviously an infinite collection of them, and that's the set of integers, and it has loads of interesting properties. You know, people who study the integers care about things like factorization and primes and composite numbers and so on, and there's loads of interesting and mysterious things to do there, but it's not quite our purpose here. But so that's kind of the starting point, I suppose, as a number system. Okay, integers are real numbers, but not all real numbers are integers. Okay, that's the integers. Okay, and just to think about the integers as a sort of geometric object, and we'd imagine that we have, you know, our number line, and that we can arrange the integers along the number line. So here it is, and on the number line, the integers are evenly spaced points. I mean, this is not news to anyone. I do realize that. But I suppose the reason for bringing up these things that we've all known about for so long is that we're going to compare how the set of integers looks on the number line to how other number systems do. So on the number line, you know, we've got zero, sort of, if we sort of decide on a distance for separating consecutive integers, maybe whatever, 1 centimeter to the right of that or whatever. In our picture, we've got 1, then we've got 2, 3, and so on. We've got -1, -2. The numbers decrease as we travel to the left, and they increase as we travel to the right. And the whole picture is imagined to be an infinite thing extending infinitely to the ends of the universe in both directions. So that's what the integers look like. And I suppose the key point here is that the integers are evenly spaced on the number line. Between each integer and the next one, we have a gap. And that gap is the same for every pair of consecutive integers, and it's just like a set of evenly spaced points the whole way along this infinite line. And one of the things that means is that, you know, if we imagine the line as being sort of a continuous thing, which we haven't yet sort of said what all the other points on it stand for, but, you know, there are sort of sections of the number line like this that don't have any integers in them. You know, there's no integer in that bit that's colored blue there. Okay, that's fine. It's not exactly a profound statement because we all, you know, it's just saying that there's no integer between -1 and 0, which is not news. But nevertheless, we can observe that there are these sort of little pieces of the number line that don't have any integers in them. And that becomes a bit more interesting when we observe that that's not the same for other number systems that we'll look at. Okay, so that's what the integers look like. They're these evenly spaced points. Okay, great. And of course, fact that they're spaced like that kind of describes the order relation on the integers. And what I mean by the order relation is that if you take a pair of integers, like minus 17 and 42 or something like that, one of them is greater than the other. And that's represented geometrically by the fact that the one that's greater is to the right of the other one on the number line. So, given any pair of integers, they're represented by a pair of points. So this maybe this is minus 17, and this is 22 or something like that. So minus 17 is less than 22, and the point that represents it is to the left of the point representing 22 on the number line, which again is not a very it's not news to anybody here. But one remark about the order relation on the integers is that the integers have this property that's called well ordering. And if you haven't come across that term before, don't worry at all. I wouldn't expect that you have, but what it means is that given any integer, like given the integer 16, for example, and again, this looks like a statement of the very obvious. If you look at the integer 16, there's a next integer after 16, which is 17. If you take the integer minus, so the next integer after 16 is 17. The next integer after minus 15 is minus 14, and so on. Okay, so again, like this is not new, but it does capture a property of integers that's not shared by other number systems. It's not shared, for example, as we'll see in a minute, by the rational numbers. The next integer after 0 is 1. But if you ask yourself, what's the next rational number after 0? That's a different question, and it doesn't have a straightforward answer. Okay, so the integers have this sort of well-ordering property, which is not only are all the integers in an order relation relative to each other, which means if you take any pair of integers, one is less than the other, or they're both equal to each other, and that applies to every pair. But not only that, but you can sort of arrange them from left to right in order along this number line, where they're evenly spaced. Okay, and that's it doesn't look like a remarkable property until you look at number systems that don't have that property. Okay, even though they do also have order relations. So the next integer after 3 is 4, and so on. So yeah, why is this property worth bothering about? Well, I think it becomes a bit more convincing when you notice that it doesn't hold for the set of rational numbers. So let's kind of leave the discussion of the integers there for a minute, unless anybody has a question or comment, in which case throw it into the chat or use the audio to ask. And we look at the set of rational numbers and kind of think about how that looks in comparison to the integers, because it looks quite different, even though it's a closely related system of numbers arithmetically. Okay, so anybody have a comment or question right now about the integers? Okay, so Z for integers, Q for rational numbers. And if you have forgotten what the rational numbers are, do not worry, we're about to recall. So a rational number is any number that can be expressed as a fraction with integers as the numerator and denominator, and the denominator obviously not being 0. So basically 2/3, 17 over 4, minus 23 over 1000, anything like that. Anything that can be written as a fraction involving integers. So the rational numbers, of course, arise in a very natural way from the integers. And again, I mean, people, there are people who work on the history of mathematics and sort of devote their lives to studying the history of the invention of these number systems independently in different places in the earth, in different civilizations, and and exactly how these systems all evolved from each other. So now, kind of where we are in the evolution of mathematics, it seems like a very natural thing to define the rational numbers, having defined the integers, because I guess you invent the natural numbers for counting, and then once you sort of realize at some point that if you want to be able to subtract natural numbers from each other, well, you need negative numbers, so you invent the integers, and then you start thinking about division, and initially maybe you can say, well, I can divide 12 by 4 and get 3, but I can't divide 15 by 4. I need some. If you want to be able to do that, you need some kind of fractions. So it's kind of a natural evolution when you want to develop a notion of division, to introduce fractions and call them numbers. And if you want to divide something up into 5 pieces, maybe it's useful to have the concept of 1/5. So the rational numbers sort of evolve, and we realize that we can add them and subtract them, multiply them and divide them, and they have all this arithmetic structure. So the set of rational numbers is the set of all numbers of this type, A over B, where A is an integer, B is an integer, and B being a denominator there, of course, can't be 0. So, examples of rational numbers are 2, which is if you want to explicitly write it as a fraction, you can write it as 2 over 1, 15 over 4, minus 24 over 167, whatever, anything at all that can be written as a fraction. Okay, those things are all rational numbers. And yeah, great. And I suppose if we allow ourselves to use rational numbers, we can certainly do a lot more than we could do if we just had integers, because the it allows us to have a sort of much finer distinction between different numbers. And in terms of the number line and how the rational numbers look there, let's just think about that for a minute. Okay, so Q, the set of rational numbers. Okay, I should have said Q. The notation there, Q is for quotient. So quotient is a word for fraction. That's where the Q comes from for rational numbers. I guess the rational numbers are not called R because R is kind of reserved for the real numbers. So the rational numbers are denoted by Q, and that's a totally, it seems to be I think it's a worldwide convention that Q is used for the rational numbers. So, okay, so there's just some examples of rational numbers. It includes all the set of rational numbers includes all the integers. I suppose if we're doing computation, which we spend a lot of time doing, and if we're trying to represent quantities, then you need to kind of have numbers that you can compute with. So rather than sort of philosophical descriptions of what your numbers mean. So in terms of their decimal representations, the rational numbers are exactly those numbers whose decimal representations either terminate in a string of zeros after some point, or repeat. So I guess terminating in a way is an example of repeating with a repeating pattern of zeros. But so if you like, you could say just those whose decimal expansions repeat. But so for example, if you have like 7.12121212 with a repetition of that 12 indefinitely, that's an example of a rational number. If you have a number whose decimal representation terminates after some point in a bunch of zeros, that's a rational number. If you have a number whose decimal expansion is just a haphazard sequence of digits with no repetition or termination, that is not a rational number. Although, of course, that's a description that is philosophically sensible, but completely useless in practical terms, because from any initial part of a decimal representation that you can write down, it's like you can't tell whether it repeats or terminates or not, because you can't write down the entire thing. So, but that's a characterization of rational numbers. And if you're interested in this, like a nice challenge is to try to write down a proof of that statement, which involves two things. Basically, that if you have a number whose decimal representation either repeats or terminates, then it is rational, that it has a fraction representation with integers. And that if you have a number whose decimal representation doesn't have a repetition in it, like an infinite repetition of some string, then it's not rational. So it's not the easiest thing in the world to prove this statement, but if you're interested in it, it's a nice one to think about. Okay, and then there's just a remark there. This is another thing I suppose I'll just highlight for your attention, is that the statement that Q includes all the integers can be written in this extremely concise way, by saying that Z, the set of integers, is a subset of Q, the set of rational numbers, which is, has the advantage of being very concise and quick to write. A remark for me is just that I think it takes a bit of time when you're learning mathematics to kind of get yourself into a way of thinking of reading a statement like this. It says a lot of things really. So it says that Z is a subset of Q. That's what it says explicitly. But there are so many ways to think about that. One of the things it says, for example, is that every integer is a rational number. And sometimes that's a useful way to read that statement. It says that the set of rational numbers contains the set of integers as a subset. And that's sometimes a useful way to read the statement. So quite often, sort of very concise statements like this, that can be written with just 3 characters, kind of contain a wealth of information, and sometimes kind of different ways of stating it with different emphasis that can kind of highlight different things. Like this says something about every integer, that every integer is a rational number. It says something about the set of rational numbers, that it includes the integers as a subset. And sometimes a kind of different way of saying the same thing, although their logical meaning is the same, can kind of emphasize different things that can be helpful in different contexts. Okay, so that's the rational numbers. And yeah, okay, so like there are loads of them, obviously. And when we look at the geometry of the integers and the rational numbers on the number line and compare them, this is something I think that's worth kind of spending a little bit of time thinking about. And probably what I said earlier about the integers doesn't seem particularly remarkable when you only talk about the integers. But when you compare it to the picture for the rational numbers, it looks a little bit different. So okay, Rational numbers can be written as quotients or fractions with integers, integer numerators and denominators. So the set of rational numbers and the set of integers are obviously closely related things. You know, the rational numbers are basically constructed from the integers by allowing ourselves to write down fractions. But on the number line, these sets as kind of geometric objects, and what I mean by a geometric object here is like a collection of dots on the number line. They don't resemble each other at all. So the integers, as we've already seen, are spaced out along the number line with intervals between them. But there are no stretches of the number line that are without rational numbers. Okay, so there's a picture on the next slide to kind of try to indicate what that means. So, you know, we saw we've had this picture already. The integers are like this. It's a 0, 1, 2, 3, and so on, -1, whatever. And of course, in between 0 and 1, for instance, there are plenty of rational numbers. There's a half, there's a quarter, there's 3/4, there's 1/8. There's loads of rational numbers there between 0 and 1. So in this little stretch that doesn't contain any integers, there are plenty of rational numbers. And that's what I mean by saying there are no stretches of the number line that are without rational numbers. Let's see if we believe that. So the assertion here is that the rational numbers are densely packed into the number line. And the term dense here is obviously has a familiar meaning in English, but also has a precise mathematical meaning. But here it's used as kind of kind of both ways, really. We're not going to bother with the precise mathematical meaning of dense at the moment. But the idea that the rational numbers are densely packed into the number line is in contrast to the integers, which are evenly spaced. So the integers are evenly spaced. And the rational numbers are densely packed into the number line. So let's see if we agree with that. So here is a picture, which is supposed to be a sort of a picture of part of the number line, a part that includes the section between 1 and 2, which are integers, of course. And so there's the integer gap between 1 and 2. We're zooming in on it a bit. And between 1 and 2, the claim is that we can pack in as many rational numbers as we want. So that in contrast to the integers, the rational numbers are densely packed into the number line. So certainly, like halfway between 1 and 2, we have the rational number 3/2, which is 1.5. Okay, 3/2 is 6/4, and 2 itself is 8/4. So halfway between them, we have 7/4. And of course, you don't have to do this halfway thing. It's just one way to illustrate the point. 3/2 would be 12/8. 7/4 would be 14/8. So in between them, we have 13/8, halfway between them, which is this point. And so on. You can keep playing this game. You know, 13/8 would be 26/16, whereas 7/4 would be 28/16. So in between them, we have 27/16, and so on. You can keep pushing in more and more rational numbers between any pair of rational numbers that you have in mind. You know, just sort of scale up the fraction by some common multiple above and below, until there's room for something else in between. So, you know, to put something between 3/2 and 7/4, write both of them with a denominator of 8. So you've got 6/8. Sorry, you've got 12/8 and 14/8. 13/8 will fit in between them, and you can keep playing this game if you want to write a bunch of rational numbers in between 1. So there's 1, which is, let's say, 4/4. Here's 3/2, which is 6/4. Here's 5/4 in between them. If you want to pack in more rational numbers in between 1 and 5/4, you can, of course, do it. No problem at all. Okay, write 1 as 8/8, write 5/4 as 10/8, put 9/8 in between them, and away you go. And you can keep doing this. You can keep packing more and more of them in, and you can sort of zoom in on any tiny part of this picture and pack it up with rational numbers. Okay, so that's the idea of what I mean by densely packed. So on any section of the number line, no matter how short it is, you can zoom in on it and pack it full of rational numbers. They're you know, no matter how small it is, no matter how many rational numbers you want to put in there, you can do it. And there's always been more of them. You can never complete this exercise by filling in all the rational numbers. So this concept that the rational numbers are densely packed into the number line is something I think that's really kind of worth thinking about. And if you find it helpful to do a kind of explicit exercise like this, like what's suggested here, to kind of give yourself a tiny stretch of the number line from whatever, from 0 to 1/5, or from whatever, anything you want really, from 7 over 4 to 8 over 4, whatever. Pack it full with rational numbers to persuade yourself that you can do it. If you don't find it helpful to do an explicit exercise like that, but you find it easy to just see it and think about it, that's absolutely fine as well. That exercise is a suggestion in case you find it helpful. Okay, so the other assertion, and this is in contrast to the integers as well. So, this statement that the integers are well ordered, I think when I first saw it, I thought, okay, well, like, why are we making a song and dance about this? It's just complicating something that's clear to everybody. But I think it becomes more interesting when you observe that the set of rational numbers is not well ordered in the sense that the integers are. So what that means is that given a particular rational number, there is no next rational number after it. And so again, like if you take two rational numbers, they are ordered relative to each other. One of them is less than the other one. And if they're written as fractions and they're not the same number, then you'll be able to write them with the same denominator. And when you do that, you'll be able to see which one is greater than the other one. It might not be immediately clear at first glance if they've got, which one is the greater, but you can figure it out. You can answer that question. So the rational numbers are what they call totally ordered, in the sense that given any pair of rational numbers that are different from each other, one of them is to the left of the other one on the number line, one of them is less than the other one of them is greater than the other one. They're ordered along a line in that sense. And there are no pairs of them that you can't decide which one is less than the other. But it is not true that they're well ordered in the sense of the integers, which means that given a particular rational number, there's no next rational number after it. And so, for example, if you ask yourself, here's the number line again, and let's take 1 as an example. The example you pick doesn't have to be an integer. Take 1/2 or 1/12 if you want to, or whatever you want. And if somebody asks you, like, what's the next integer after 1? But that's easy, it's 2. But if somebody asks you, what's the next rational number after 1? Well, that's not easy, because as soon as you take the tiniest step along the number line to the right from 1, you've already passed by loads of rational numbers, no matter how small the step is. Okay, so even though there are plenty of rational numbers and they're all there on the number line and they're all kind of ordered from left to right, you can't say what the next one is after any particular given one, because as soon as you take a tiny step to the right of where you are, you've already jumped over infinitely many rational numbers. So there's no sort of candidate that you could write down. If you had some candidate in mind, let's say 1.000001 for the next rational number after 1, or 1 plus 1 over 10 million or whatever. Well, it's not, because there are other ones that you could squeeze in between. If you say 1 plus 1 over 10 million, I could say 1 plus 1 over 100 million. Okay, and that's nearer to one than your example was. But then you can say 1 plus 1 over 20 billion, and that's nearer again. Okay, so as soon as we take a tiny step, the tiniest step, a tiny step along the number line to the right from 1, from 1 or any other rational number, doesn't matter what it is, we've already passed by infinitely many rational numbers. We've already passed by infinitely many rational numbers. Okay, and that's kind of another way to think about this comment, that the rational numbers are densely packed into the number line. There's no part of the number line, no matter how tiny, that is without rational numbers, and that's different for the integers. Like in the part of the number line between 1 and 2, there's a chunk there of the number line that has no integers in it, and that's kind of related to the idea that given a particular integer, you can sort of travel to the right until you meet another integer, and the first one that you'll meet, if you start somewhere between 1 and 2, is 2. But you can't sort of travel to the right until you meet a rational number, because as soon as you take the first thought of traveling to the right, you've already met infinitely many of them. So they're just so that's what it means to say they're not well ordered. So this idea of being well ordered is kind of related to the idea of being kind of spaced out, that there are gaps between successive integers. Now, if you take, for example, all the rational numbers that can be written with a 2 as their denominator, so you have like a half, 1, 1.5, 2, 2.5, 3, and so on. Those things are spaced out. They resemble the integers. But if you take all rational numbers with all possible denominators, they're densely packed into the number line. Okay, so that's I've kind of probably labored the point a bit, but it's really an important contrast between the integers and the rational numbers. And of course, the rational numbers are an incredibly useful number system. and they're the number system that we use all the time if we're doing any sort of calculations or computations. And they're the, they're not exactly the full number system that computers use, but they are. But the numbers that computers generally use are rational numbers. They use decimal approximations, truncated decimals, or whatever, which is I mean, the whole subject of how computers deal with numbers is another whole interesting subject in its own right, as many of you probably know if you're interested in computer science. But certainly, the numbers that computers can deal with, by and large, generally are rational numbers. Okay, we have a couple of minutes, so let me say a little bit more. Okay, we're supposed to be talking about the real numbers, and so far we've talked about the integers and the rational numbers. So now we have, now think about the real number line again. So it's an infinite straight line, typically drawn as being horizontal, although I don't know exactly why it has to be. It could be drawn vertically. And the integers are marked on it as evenly spaced dots, 0, 1, 2, etc. And they're evenly spaced the whole way along. They don't sort of get compressed as you travel further out or anything like that. And the rational numbers, we know we can represent also, like, 1/2 is the dot that's halfway between the dot for 0 and the dot for 1. So supposing that you also imagine that the rational numbers have been marked by dots. And so we have a scheme for saying where the dot should be that represents a given rational number. The rational number 1/141 should be like 1/141st of the way from 0 to 1. And so we'll imagine the rational numbers also, as well as the integers, have been marked by dots. So halfway between 1 and 2, we have the dot representing 3/2 and so on. And we've got loads and loads of them, as we've seen. These dots are densely packed into the line. So at this stage, an awful lot of dots have been marked. And every stretch of the line, no matter how tiny it is, contains an infinite number of marked dots, marking all the rational numbers in there. And this is kind of conceptually difficult to get a handle on, I think. But there are many points on the line that still aren't marked. And maybe a way of thinking about this is, if we think about numbers as being represented by decimal representations, and we have in our minds the idea that a decimal representation of a number might not have a termination or a repeating pattern, that it can just be a sequence without any, discernible pattern of digits 0 to 9. And so you have numbers like pi that just continue infinitely without repetition, without infinite repetition of a string. Then somewhere in this number line, somewhere to the right of 3, between 3 and 4, a bit more than 3.1, is a dot representing the number pi. Okay, and of course it's not obvious that pi doesn't have a rational representation, but we know it doesn't. And it's not one of these dots that has been colored when all the rational numbers have been colored. So a lot of dots have been marked. Every stretch contains infinitely many marked dots. So you have this like dense mist of colored points on the line representing all the rational numbers, but there aren't points on the line that remain unmarked. For example, somewhere there is a point representing pi that wasn't colored when all the rational points were colored. And somewhere there is a number, is a point representing the square root of 2, which is definitely a real number because it's the length of the side of a triangle, which has a right angle and two sides of length 1. So that point also, we're going to see shortly that the square root of 2 is not a rational number. That point also hasn't been colored. So the set of real numbers is a set of numbers corresponding to all points on the number line, whether they're marked by their fractional representations or not. And that's something, I guess, again, that is not news to us, like we've been used to this concept of the real numbers. But I suppose the point here is that the number line, every point on it represents a real number. And some of them are rational. A lot of them are rational, because when you color all the rational ones, it sort of looks like the whole line is colored, because every tiny part of it is full of colored points. But there are still points there that haven't been colored after you've colored all the rational ones, and they're the irrational real numbers. And so we'll be talking next time we meet about the distinction between rational and irrational real numbers. And that's something that's of interest in analysis and in calculus. It's of interest also, of course, in algebra and in number theory. And but one of the things we'll be looking at in this course is, how do you answer questions with, like, are there more rational numbers than integers? Okay, it looks like, yeah, there should be, because like the rational numbers are densely packed into the line, but the integers are evenly spaced out. They're kind of a sparse set. But what would it mean to say that there are more elements in one infinite set than in another? Are there more irrational numbers than rational numbers? Are these questions that we can even make sense of? Does mathematics have the machinery to make sense of these kinds of questions? And it didn't for a long time, but it does now, as of approximately 120 years ago or so. And we're going to talk about that in this chapter. And so, yeah, we'd be interested in these different infinite sets. How do we compare them? How do we deal with questions like, does one of them have more elements than another? On the one hand, the rational numbers is a much sort of richer set of numbers than the integers, because we can approximate any number like pi as closely as we want to by using rational numbers. Just take truncated versions of the decimal expansion of pi. But in another way, we'll see as we go a bit further, another very explicit way, there aren't more rational numbers than integers. If we think about the actual sort of trying to enumerate the elements of both sets. So those are the kinds of things that we'll be interested in. I should really stop talking because we're pretty much out of time. So actually, I'm going to finish the recording here and thank everybody who has joined us for the recording. And also just make the comment that next week we'll meet on Thursday, not on Wednesday, because next Wednesday is a public holiday. So next week we'll have just one lecture on Thursday. And I hope that everyone has an enjoyable break in the middle of the week next week on St. Patrick's Day. So we'll leave it there for today. Thanks to everyone who's joined us for the recording, which I'll stop now.